So let's get started. So last time, if you remember, we talked about invariant in cosmology, coordinates that we use in cosmology. And if we talk about in 3 dimensions, we use x, y, z, right? X, y, z coordinates. But that is not so convenient in expanding universe because expansion is in a radial direction. So we talk about its, okay. Before that, we put this time because in general relativity, Einstein's relativity, time and then space are, the same variable, relative thing, right? So we need to include time, dt here. And then we talked about that this xyz coordinate is not convenient for spherical universe, because universe expansion is spherical in this kind of thing. So it's better to use spherical coordinates. So r, theta, and then phi. Theta and phi are the angle. That's more convenient when the size of the universe is changing. So we think about this variance. And then because the universe is expanding or changes the size, at the moment it's expanding, it's more convenient to put the scale factor here so that when the expansion of the universe can be parameterized this, not changing r all the time. So these are theta phi are to describe relative distance between galaxies, right? And then this r, large r, is a scale factor of the universe, so that's separate thing, right? Motion of galaxies and expansion of the universe, if you separate, that's more convenient. So we put r, and then the curvature. So universe may be flat or maybe flat or closed, open. Geometry of the universe is not necessarily flat, so we need curvature term k, right? And then we reach this one. So this is the famous Friedmann-Robertson-Walker metric. This is the simplest metric for the spherical expanding universe. This is the simplest form to make your calculation easier. Okay, then we put this into Einstein equation. So Einstein equation is just saying, curvature tells matter how to move, and then matter tells space how to curve. Gravity can curve the space, so that's equal. That's Einstein equation, right? And then we don't do this in this class. If you take general relativity class, they will teach you. But we use Einstein equation. So we put this in this Friedmann metric into Einstein equation. So we put this thing into Einstein equation, and then we will get these two. Derivation is lengthy, so we don't do it, but we get this. So these two are famous Friedmann equation, and then these two equations will describe the expansion or history of the universe as we see in the class whole semester. Okay. What I want you to do is, you don't need to remember these, but I want you to understand where this came from. We put the Friedmann-Robertson metric into Einstein equation, and then we derive this Friedmann equation. That's the equation we need to do cosmology. Okay, that's what we did the last week. And then here. So we start a new topic here. In the expanding universe, there's something interesting happens. Something like the time dilution. Okay, the clock here, and then clock at very distant universe, say relative to 1, 2, are not, same, not ticking the same. Let's see this example. So let's see there are 2 photons T1 and T2. Well, suppose this is a distant galaxy, and then there's a distant galaxy, there's an alien, and then it flicks the light 1 time, 2 times. Okay, then photon 1 travels through the universe and then reaches us at the time t0, okay? And then later, delta t later, this alien is going to emit second photon, okay? And then the second photon is going to travel to us and then reaches us. But then here, the program or interesting thing we need to think about is the universe is expanding during this time, right? So in alien point of view, this is delta t, or let's say 1 second. So it freaks a light, and then 1 second later it freaks a light, right? It's just 1 second. But it's not 1 second for receiving part for us, because during this 1 second, delta t, universe is expanding. So when alien emit the first light, alien was here, so it only need to travel this r1 distance. But then by the time 1 second later, when alien emits second photon, the universe has expanded a little bit, right? So this second photon needs to travel a little bit longer distance than the first photon, right? So the time for this intervening time between photon 1 and photon 2 is not delta t, but you can imagine it's longer than delta t, right? How much longer? How much longer is just the speed of the light is the same, right? That's from general relativity. It's just c, right? So it's just proportional. The delay is time difference is just proportional to the ratio of this and then these two distances. Okay, so if distance is twice as large, this time is twice long, it takes twice longer, right? If this is 3 times longer, this time takes 3 times longer time, right? Does it make sense? So the delta t is the time between first and second photon for alien, but for us to see, it's not delta t anymore, it's R0 R1 times c delta t. So there's a factor of this ratio of the distance, right? So this is called, time dilution, okay? So, for example, say AGN, say Leeds likes AGN, right? AGN is, exploding every day, once a day, 1, 2, 3. But then if it's twice as distance, then we might see it's like not 1 day, maybe 2 days, every 2 days, every 3 days, something like that. So that's called time dilution. Then this ratio of R0 and R1, so this distance ratio, we define it 1 plus z. So that this z is so-called redshift. So that's, we define later, but then it's how much the wavelength gets later. So that's another definition of the redshift. And then, as you can see, this R0, I'm using the same sign, right? R1 is the scale factor of the universe. So you remember that in a Friedman metric, Friedman-Watson-Walker metric, we put the R in front of coordinates, right? So that we can scale the size of the universe. So that's the same scale factor. So see, that's convenient, right, to put it there. Okay, then now I have a test. Okay, I have many tests today. Okay, so let's say at least AGN is exploding, getting brighter every day, right? Right. Okay, so every day it becomes bright, faint, once a day. Okay, and then now that AGN is say at redshift 1. Redshift 1 means this z is 1. So this factor is 1 plus 1 equals 2, right? So now you observe this AGN at redshift 1, and then at the AGN is once a day, it's becoming brighter. So now you on the Earth, so you observe it's brightening, how long per day? How many times it gets brighter? How do I ask? What's the time between each brightening?
2 days.
Yes. Who said? Oh, Jamie? Okay, good. Thank you, Jamie. Yes, that's right. Yeah, if redshift 1, you get u plus 1 plus 1, 2, right? So a factor of 2 larger, right? Okay. Yeah, don't confuse it. So when you observe something very distant, and oh, it's becoming, every 2 days it becomes brighter, but if it's a redshift 1, it's actually becoming brighter every day, right? The time is diluted, so that's called time dilution. Okay? Then what's the next topic? Okay. Then redshift, definition of the redshift is also, we should talk about it. One way to define is the ratio of the scale factor, current and then scale factor at that time, so the distance, the ratio. And then also, because of the expansion of the universe, the wavelength of the light also gets longer, right? This is called redshift. So you can define this redshift as a wavelength of observed light and the emitted light. Because emitted light is a wave, right? Emitted light, and that's it, because of the expansion of the universe, wavelength gets longer. So how much it got longer, and you can take ratio, and then that's also definition of 1 plus z. So for example, at redshift 1, the wave, it's going to be 1 plus z with 2, right? So the wavelength is going to be twice longer, right? So, like 1 micron, the wavelength of the light becomes 2 micron if the object is at redshift. Okay. So actually, people use redshift z, but then actually, what physical is 1 plus z? Because 1 plus z tells you factor of how many universe is larger or wavelength is longer. Okay. So that's the definition. Okay, then okay. One caution is redshift is not a recession. So okay, when people talk about redshift, people talk there's something similar is Doppler effect, right? When ambulance comes in, frequency gets higher, and when ambulance goes far away, frequency gets longer, right? It's similar, but it's not the same. Because in ambulance case, ambulance is going farther away, right? It's actually literally moving away. But then redshift is because of the expansion of the universe. So that's not exactly the same. Okay. Then here's a side story a little bit. Nowadays we know the universe is expanding because Edwin Hubble, 1929, he discovered the expansion of the universe, and we know that the universe is expanding. But at that time, the 1929, a lot of people, even Einstein, didn't believe universe is expanding. So, but then people already know that distant galaxies are redshifted. The light of distant galaxies are becoming redder, right? And so people are wondering why. Then this guy, Zwicky, famous one, he's the one who discovered dark matter, came up with a hypothesis. But okay, the light might get tired when it's traveling very long time. Okay, maybe some people are laughing because we know it's not true. But at the time, people seriously thinking about this kind of story. But then, if the light just get tired and becomes redder when traveling very long distances, it doesn't cause the time dilution, right? And this time delay, time dilution. Time dilution is only caused because of the expansion of the universe. And then now, here's the supernova observation data. So this is decay time. So supernova explodes and then becomes fainter, right? It's, for example, type 1 supernova. This is about 2 weeks. supernova explodes, and then it takes 2 weeks. 2 weeks later, it becomes fainter. And then this is normalized. So this is 1 point, it's different supernova as a function redshift, and then this, say 1.0 is normalized, so it's about 2 weeks. And then the question is, if this Zwicky's tired light theory is correct, this should be flat, right? But then, when you go to distant universe, the time gets longer and then longer and then longer. This is exactly as a function of 1 plus z. So that time dilution, you can observe it in a supernova data in this case. So that's the proof that the Zwicky's tired light theory is not correct. Cannot explain this. That's one example. Okay, so this is saying supernova explosion is always 2 weeks, right? But then in very distant universe, very high redshift, it takes more than 2 weeks. So that's the evidence that the time dilution is happening. That's because of the expansion of the universe. Okay, and then this is another example of emission lines. So this is, let's look at this. This is oxygen excitation line, which is actually 500 nanometer. Okay, oxygen excitation line. This is oxygen atom, and it's ionized and it comes back and it emits the light, right? That's decided by the energy levels of oxygen atom, so it's always at this 5,000 angstrom. Okay, but so this is nearby galaxy. If you observe, and then this galaxy excites oxygen, it's here to emission. Okay, but then let's look at in this case, this is distant galaxy, and then how do I magnify this? Can I magnify this? I don't know. Okay, I don't know. In this case, I can read this is 8,000 angstrom. So the same oxygen line, it should be supposed to be 5,000 angstrom, but now it's 8,000 angstrom. That's because of the redshift. This 1 plus z, we push this to here. So if 5,000 angstrom becomes 8,000 angstrom, what's the redshift?
8 by 5.
What did you say?
8 by 5.
8 by 5? Yes, yes. So what's the number?
1.6.
Minus 1, right? 1 plus z equals 1.6. So
Okay.
minus 1, so redshift is, these galaxies are at redshift 0.6. So that's, for example, how to calculate the redshift. Okay, so that's the topic. And then we go to the next chapter. Okay, you might like this chapter. Okay. So now, I'm going to explain cosmological parameters. Good. This will be help. Because we just showed that Einstein, Friedman equations, right? And there are a lot of parameters, right? You don't like that, right? I'm going to reduce it into 3 parameters. Very simple, right? You can even remember. Okay, let's do that. So now, we talk about scale factor. Okay, scale factor becomes twice as large, universe is twice as large, right? But we want to relate this scale factor to real distance, don't you? Don't think this factor is weird, right? We want the unit. It's a kilometer or millimeter or kilometer, or in astronomy we use parsec. That's the distance. So we want to relate it. And then it be like this, right? Scale factor and then some factor, constant, and then that's going to be distance with a unit. Okay. And then this part should be constant, but the scale factor is as a function of the time. So if we take a derivative, okay, that tells you the expansion speed, right? So this is distance, and then distance time derivative, that's speed. And then this is constant, so it's actually proportional to scale factor time derivative. So actually, scale factors time derivative tells you the speed of the expansion of the universe. And then, okay, it becomes, if you put something like, if you change it like this, and then you can write it this part, something like this. R dot time derivative divided by R, and then you can write it, this L is a, this should be D. So I'm sorry, this is, no, we change it. We put this in here, right? Sorry, this D is replaced by L by R. So this part is D, right? D is this, using this. So that's why L is here. And then, so time, the expansion speed, we can write it L times here, this R dot divided by R. And then we define this as a Hubble parameter. So that's the definition of Hubble parameter. And then the current value, that when we write 0 here, that's a current value, present time, not in the past, present. So that's called Hubble constant. So maybe you have heard of Hubble constant, right? The definition is here. So the R dot divided by R is the Hubble parameter. And then that's telling you the expansion speed of the universe. One caution is, okay, maybe you have heard Hubble constant, but it is not a constant at all. This is, as you can see, it changes as a function of time. So Hubble parameter is maybe a better way to say that. And when we say Hubble constant, it's talking about the present value. So present value is 1, right? Time is now, and it's a Hubble constant. So of course, the Hubble parameter's value changes as a function of redshift over time. Okay, then now, and then when this time is very small, when in a very nearby universe, when distance is very small, we can regard this part as a constant. Okay, and then it can be velocity v equal L times h, and then this is called Hubble constant. Of course, this Hubble parameter is not constant. So when you go to higher redshift or very distant universe, this is not a constant, so you cannot use this. But in a very small time interval of very nearby universe, you can regard it as a constant. And then you can use it as, this is what Edwin Hubble discovered. Hubble diagram is so Hubble diagram is something like this. You take a distance and then velocity, and then you put gases, and then it's like this. So this is Hubble diagram. And then this slope is Hubble parameter. So this Hubble diagram is how Edwin Hubble discovered the expansion of the universe. The more distant galaxies are moving away from us faster, and that's because the universe is expanding. And then this Hubble parameter tells you the slope of this relation. See, this is exactly Hubble is. This is distance, right? More distant, velocity is faster. And then, y equal ax, right? So this slope is Hubble parameter. Okay? All right. So now, one parameter down, so that's Hubble parameter. And then the unit of Hubble parameter, as you can see, it's something like this. Velocity divided by distance, right? Because velocity divided by distance is the unit. And then sometimes we use h, small h, by normalizing, dividing it by 100. And then the current value, the best measured value, it's something like 17 for Hubble constant. In a small value, it's 0.7 also. You might know there's no final conclusion on this. Some teams say it's 72, and then some teams say 68, and there's still a lot of controversy over there. Okay, fine. We can talk about it another opportunity. Okay, now we divided, right? We decided, right, this, right? So now we go back to Friedman equation to describe the universe. So that this was Friedman equation from here to here. And then, as you can see, this R dot divided R, what is this? What is this? R dot divided R. Julie. Okay. Is this R dot divided R, is this, is this cosas parameter? Yes. Is this Jamie parameter? Yes. No. This is Hubble parameter, right? This is Hubble parameter. We just defined, right? So we can write it down h squared. So the Friedman equation, if you divide R squared, it's going to be h2 equals. And then now on the right part is too complicated, right? So you don't like that, right? So we simplify that. So we defined this as omega matter. Okay, we need to divide this by h squared. And then omega radiation is this part is just omega radiation, omega r. And then this part divided by h squared is omega lambda. And then this part, k, divided by h squared is omega k. And then we just use these omega mr lambda k to describe Friedman equation. And then voila, it's very simple, right? Now before it's complicated, but now it's very simple. Omega matter to omega radiation plus omega lambda to omega kappa is 1. That's Friedman equation. That's much simpler, right, than this. Okay. What this is saying is this is energy budget of the universe. So omega ion is mass, right? This is density, right? Mass density. So how much dark matter and then regular matter are in the universe. Omega radiation is the light, CMB light. How much radiation is right. But this is very small, so actually we can ignore this. The present day, this is very small. At the time of Big Bang, this was very large, but now it's small because universe is expanded and then photon lost the energy. Because photon wavelength gets longer, right? So photon loses energy by the power of 4. So it quickly becomes very small. And then omega lambda is this dark energy that's pushing the universe away to expand. That's dark energy. And omega curvature, so this is geometry of the universe. But omega curvature is also very small that we know. So actually, the universe is, if you ignore this and this, present day, omega matter, dark matter, and omega lambda, dark energy, is doing a tug of war. If this part is bigger than this, universe is going to expand. And this omega matter is bigger than this, universe is going to shrink because gravity is going to pulling force. And then we're going to see it, so maybe next week, but at the moment, as observation tells us that omega lambda is larger, so universe is expanding. Okay? So you like this? Friedman equation, this becomes this. That's simpler, right? Okay. Okay. So, okay. I wrote down this is the current measurement of those parameters from the Planck cosmic microwave background observation, Planck satellite observation. And as you can see, Hubble parameter according to Planck, it's something like 67 or something like that. And then omega lambda is 0.7, omega matter is 0.3, and then they don't even write omega curvature and then omega radiation because it's very small. Okay, good. Okay, and just so you know, this parameter, it was everywhere, right? 3h naught 8 pi g. It's here, right? So this is called critical density, and then this value, omega matter, is larger than this or smaller than this, is actually going to decide on curvature of the universe. If the value is this larger than this, I forgot which way, it's going to be closed universe, and then if its value is smaller than this, it's going to be open universe, the geometry. But very fortunately, the density of the universe is very close to this, so our universe is flat. So that's very, God is very kind to us. Our calculation is very easy because of this. Okay. Okay, and then now maybe you notice here, age of the universe is 13.8 billion years. That's the age of the universe. How do we calculate this? It's not one of these parameters, right? So how do we calculate this? Is this? So, okay. Now, calculation is very long here. So, we just try to understand how. Okay, we don't do actual calculation. Only Alex does actual calculation. Okay, so the Hubble parameter, we define it's R dot divided by R. So this is definition, right? And then Friedman equation, we now replace with omega parameter, so that's easy, right? So we combine these and then long calculation. Here's a long calculation about 1 page. And then you get to here, okay? What you need is, you want to describe dz as a function of time. This is redshift as a function of time. So basically, this is still Friedman equation, right? And then now you calculate this parameter. You express this with z and the cosmological parameters. Here's omega matter and then omega lambda and then z, right? So what you want to do is, this is delta z, delta t. So if you want the time, you integrate this with z. And then you can do that, right? Because z is here. And then these are parameters. So you can integrate this. Once you decide these parameters, you can integrate, right? And then if these parameters are decided by Planck satellite like this, you put these parameters and then do integration, and then you get the age of the universe, this 13.8 gigayears. So that's the current estimate of the age of the universe. Okay, then, all right. So that's what we did, and then if you do that, it looks like this. So this is age of the universe, or look back time, because the time to that redshift, and this is redshift, and as you can see, the current time is redshift 0, and then as we go larger redshift, we are looking back in the past of the universe, and then this is actually how many gigayears to that time, and then we put the parameter. Let's look at this one, that close to current estimate. So at redshift 1, it's about 7 gigayears. And then if you go to here, it's close to 13 gigayears, right? And as you can see, this is not linear like this. it's like this, right? So at redshift 1 already half the age of the universe, and then at larger redshift the time goes back slowly. So actually if you compare redshift 7 or 8, there's not much time difference. But if you compare redshift 0 and 1, there's a lot of time difference. Okay. Now we have Friedmann equation, and then we can see an interesting Nancy Kerrigan problem. Do you know Nancy Kerrigan? Figure skaters? Maybe you guys are too young to know. Nancy Kerrigan is a figure skater in US. Then she was going to go to the Olympic, in a winter Olympic. Then so in the US there's a selection, right? In US championship, and then only top athletes go to Olympics, right? And on one day before this US championship game, someone came and hit Nancy Kerrigan's leg. And then she screamed, why me, why now? Why the day before the Olympic selection? Why are you attacking me, right? But the same thing is happening in cosmology. Well, this famous cosmologist, Mike Carr in University of Chicago, is good at, at these kind of metaphors, and then said that. But in cosmology, this kind of thing is happening. Well, maybe you Google Nancy Kerrigan problem, and it turned out the Nancy Kerrigan was very likely to get the first place. But this second place lady, she wanted to go to Olympic, so she hired a guy to hit her. Anyway, in the universe, it's more pure physics problem. Okay, so what we want to do is here. Okay, now we have a Friedmann equation, right? So again, this is kind of Friedmann equation. So now we wrote down the Friedmann equation. You remember this h squared, that's Friedmann equation, right? We wrote down with cosmological parameters. Now we have parameters. It's omega lambda and omega matter, amount of dark energy and dark matter. Okay. And then now you are God of the universe. You can describe the universe with this equation. We'll see. Okay. Now, what if the universe is dominated by matter? This is called Einstein Dojita universe, because Einstein thought this is something Einstein thought about. Okay. So now there's no dark energy. Lambda is 0, and there's only dark matter. So dark matter is 1. Okay. Curvature is 0. Okay. And then what happened is no problem. We can create such a universe. So what happens? This is 0, right? This term is 0, right? And then only this term. Okay? So that's no problem, right? We can write that kind of universe. It's probably going to shrink. Okay? But okay. But now, so theoretically, such universe is possible, as Einstein was thinking about. And then now, the problem is we go. Okay, now we think about the more realistic part. Okay, let's still think about omega lambda equals 0. So there's no dark matter still. And let's reduce the amount of dark matter, not 1, but then 70%. Okay, 70% dark matter. Okay, then what happens? Then, we again skip the calculation, but you put this number in this, and then go back time. That's what you do. And then, let's say, if you go back to redshift, say 1000, omega matter is going to be 0.9996, but not 1. Okay, so basically, if you go back at redshift, if you go higher redshift, omega matter is going to be close to 1, and then omega curvature is going to close to 0. Okay, but not 1. This is a weird number, isn't it? 0.9996. It's so close to 1, but not 1. That's weird, right? And a more weird thing happens in our best estimate of parameters. Okay, let's say dark energy is 70%, 0.7. Dark matter is 0.3%. These are the current best estimate, right? Then we go back time at higher redshift, higher T. Then what happens? Then at redshift 1000, omega lambda should be 3 times 10 to the minus 9. And the omega matter should be 0.99996. That's weird, isn't it? Omega lambda is very small number, 10 to the minus 9, but it's not 0. And the omega matter is very close to 1, 0.99996. It's very close to 1, but not 1. Something weird, right? And actually, if you do the calculation, it's going to be like this. So this is matter of omega matter, omega lambda, right? And this is at the beginning of the universe, and now we are here. Okay? And then our value, best observed value, is somewhere around here. So in terms of omega lambda, this red one is 0.7. Okay? Am I right? What? And then this, right? This should be 0.3. Okay. And then you go back, and then you go back time, and then omega lambda goes very close to 1, but not exactly 1. Okay? Sorry, omega matter goes very close to 1, but not exactly 1. And then omega lambda goes to very close to 0, but not 0. And then the problem is, okay, maybe you think, okay, this may be 0. It might go to 0, right? It's a very small number. So okay, but then if you start from 0, say, let's start omega matter at 0, then omega matter stays 0. And if you start with omega lambda at 0, then omega lambda stays 0. And omega matter is 1, then omega matter stays 1. So in the very early universe, somehow omega lambda was very small, but it was not 0. There was a very small number of omega lambda, dark energy. And then omega lambda was not 1. It was not, filling the universe, but there was a little bit short. Only tiny bit like this, right? Otherwise, our universe is not going to be like this. In our universe right now, do I have this? Okay. In our universe, our value is here. And then this is why we can exist here. If the universe is dominated by dark energy, omega lambda, then everything is expanded, and then the sun and the earth cannot form, and our body cannot form without the earth. So we're not here in this kind of universe. And then if the universe is dominated by omega matter, then everything's going to be black hole, right? If the gravity is too strong, we cannot exist. Everything's going to be black hole. But in our universe, this omega lambda and omega matter is sort of balanced, 0.7 and 0.3. These are comparable, right? It's not like 1000 and then 0. or 1000, it's a comparable number, right, in order. And that's why it's balanced, so dark matter and dark energy is balanced. So that's why we can exist here. Dark energy, the repulsing force, and dark matter, gravity is balanced. That's why we can stay here. But to make that, in the early universe, very fine tuning is needed. This number, this very fine-tuned number is needed in the very early universe. And then we don't know why it happened. Because isn't it, it's more natural to have 1 instead of 0.99996. It more makes sense. Isn't it easier just to have 0 instead of having 10 to the minus 9? But somehow it was not 0, it was not 1. That's the reason why we're here. And this is called cosmological fine-tuning problem. It seems our universe is very fine-tuned somehow so that it's convenient for us to be here. That, it seems unnatural to many. And this is, one of the unsolved problems in cosmology. For example, if you take the exam, it's very difficult. So say you take the exam, right? You have final exam, right? And it's very difficult to score only 1 point, right? It's much easier to score 0 point, right? If you don't understand anything, you get 0, right? It's very difficult to get 1. And also very difficult to get 99, right? If you're smart and understand everything, you get 100, right? It's very difficult more difficult to get 99. But our universe is something like that. Have you ever scored 1 point in that exam? No, right? Because it's difficult, right? Okay, good. I was a little bit worried if you might say yes. Okay, that's cosmological fine-tuning problem. Okay. Okay, so actually there's no one knows the answer. So if you find it, it may be Nobel Prize. Okay. What time is it now? This class ends at 4:10, right? So maybe we can do one more topic before going to, maybe at 4 we go to 3D presentations. How about that? Okay. So then, maybe, are you tired? You're tired and becoming red light? Okay. Let's do one more easy topic. Okay. This is easy. So, next topic is, how do you measure distance in the expanding universe? Okay. So, let's think about this expanding universe. So, there's a distant galaxy, and it's emitting a light, and we are here observing this galaxy. Okay. The light starts from here, from this galaxy, and then comes to me here, right? But the problem is, during this time, the universe is expanding. So actually the light is not come from B to A. By the time light is traveling, B goes to D and A goes to C, because expansion of the universe. So the light goes from B, comes to C actually, because universe is expanding up about this. Okay, now I have a quiz for you. And then we want to measure the distance between myself and then this distant galaxy. Okay, how do we measure distance? Is it distance between A and B, or C and D, or C and B? Okay, you have 3 seconds to think about 1 to 3. Okay, who thinks distance is B to A? Who thinks B to A? No one? Okay, Who thinks D to C? No one? Please raise your hands at one of them. Okay. Now, who thinks distance is B to C? Oh, a lot of people. Oh, a lot of people. Okay, now who thinks D to A? No one? No one thinks D to A. Okay, you guys are so smart. One of the distance is in red, right? Right. This is red, right? So that's the answer. Okay. So actually, this is we measure distance from P to C. That's what we do in cosmology. There's nothing wrong with B to A and D to C. It's just a convention in cosmology that when we say distance, we measure distance this way. Okay. Then now we introduce the two ways to measure coordinates in expanding the universe. Okay, so it's how do you think? What's your name? What's your name?
My name?
You forgot?
Okay, Andy.
Andy.
Yeah.
Andy. Okay. So Andy. So what's the distance between Andy and me? Okay. Say it's 1 meter. Okay. 1 meter. And then okay, maybe I go moving away from Andy. Then that distance is getting larger, right? And then in this case, I am moving away from Andy, right? Right? Oh, I don't like Andy, so that's because I'm moving, right? That's one way. But then, when we are in the universe is also expanding. So even if I'm not moving at all, because of the expansion of the universe, our distance gets larger. And then that's different from the first case, right? First case, I was moving by myself. And the second case, I'm stopping, but the universe is expanding, so that's our distance is getting larger. The one example is, say, Andy and myself are on a carpet, it's squashed carpet. And then we're standing on a carpet, and then you pull the carpet, even I'm not moving, because of the carpet is moving, our distance is larger, right? And we want to differentiate these two cases. It's inconvenient just to measure the distance, then we don't know it's my movement or expansion of the universe. So we use these two coordinates. One is proper coordinates, and then co-moving coordinates. And then in proper coordinate is our usual way to measure distances. So it doesn't matter if it's the expansion of the universe or me moving, it's just measure it's Andy and me 2 meters, it's 2 meters. So that's using our units, physical coordinates. So if you do this, then so that's proper coordinates. And then in the expanding universe, that's inconvenient. So we often use co-moving coordinates. Co-moving coordinates expand with the universe. So the coordinates expand with the universe. So say me and Andy the distance is 1 meter, and the even expansion of the universe moves us away, it's still 1 meter, one co-moving meter. So in that way, in these coordinates, we can differentiate we can separate out expansion of the universe. So that's often we use it. Let's see the example. I often get confused. But then say this is a distance, say 1 megaparsec. And then in this time, these two galaxies are co-moving or proper motion distance, it's 1 megaparsec. And then this expansion of the universe make it larger, right? And then, because we are sitting on the expansion of the universe, now our distance get larger because of the expansion of the universe. So the proper coordinates, it's become 2 megaparsec because it's 2 megaparsec, right? It gets larger, 2 megaparsec. But even in this case, co-moving distance is 1 megaparsec because that's because of the expansion of the universe. And then it becomes now even bigger, and then, I don't know, this becomes 3 megaparsec for proper distance. But for co-moving distance, it's always 1 megaparsec. So now please make note that these two differences are not the same, right? The distances are not the same. This is 1 megaparsec in co-moving, but 2 megaparsec in proper motion distance. So, you have to be careful when someone says, oh, this galaxy is 1 megaparsec. Okay. But you need to be careful which distance are you talking about? Because these two numbers are not the same. Often, if you are talking about large distance, yes.
We usually choose now to be the co-moving distance.
Sorry, what's the question?
We usually choose now to be the co-moving distance.
When we are talking about cosmology, or very long distance, we are usually talking about using co-moving distance. But when you are talking about gravitational effect, like for example, collapse of a star or collapse of a cloud, then its gravity actually works on this proper distance, right? So you need to use these coordinates when you talk about some physical effect. For example, collapse or merger or something like this. You need physics works in these coordinates.
So when we just talking about the co-moving distance, it should be the same. Usually it should be the same as the Hubble distance now.
Yes, now it's the same. Yeah. Now it's the same. So, because so distance between Liz and me, now it's the same. Co-moving distance and proper motion, it's, I don't know, 3 meters. It's 3 meters.
Shorter in the
Yes, but if you go in the past, these two numbers are different. So, okay. Now, okay, I have 10 more minutes, so let me talk about a little bit about how to measure the co-moving distance. It's so you remember the Friedman-Robertson-Walker metric, then you remember we have the scale factor, and then this curvature, and then theta and phi. But because universe, we consider cosmological principle that in a very large scale, universe is the same in this direction and this direction. That's homogeneous and isotropic. And it doesn't depend on the angle. This universe has more galaxies than this. That doesn't happen in a very large scale. In a small scale it happens, but not very large scale. So we can assume every direction is the same in cosmology. That's very convenient, right? So we can take phi, theta, 0. Right? So there's no more complicated part at the end. Do you like that? It's very simple, right? It's very simple now, Friedman-Robertson-Walker metric. And if you remember, Friedman-Robertson-Walker metric is about the variance, how much the change in a space-time. Okay, so ds is a change, although it has a time constraint, time part. And then now, so in that sense, this is sort of distance, right? It's the little bit of shift in direction and time. So this is sort of distance. So definition of co-moving distance is just you take square root, because this is square, you take square root and then integrate. So co-moving distance definition is actually this square root. Now I took square root here, right? And then this is a co-moving distance. And then this is delta co-moving distance. So you need to integrate from somewhere to somewhere, 0 to somewhere, this part. And then that gives you the co-moving distance. This is definition. And then, okay, now we have curvature here. We don't like that, right? So if the curvature is 0, if the universe is flat, then it's just this part, R, and then R, and then integrate. That makes sense, right? This is scale factor, so you just integrate scale factor and that gives you the distance. Right. And then how do we relate to the redshift? So, but this scale factor is something you cannot observe. So we want to relate to redshift. Redshift you can observe from the emission line, right? So we want to write it down in terms of the redshift. And then, the light rate ds is 0 because light goes the shortest distance. Okay. And then radial direction we take 0 assumption, and then this is going to be this. This co-moving distance is the light passing distance. And then this, you write it down like this, transverse, and then, okay, you can just watch. Here the Hubble parameter, we put it R dot divided R, and then R, this is definition of Z, and then we put it in here, this is going to be in here, and then this is differentiation of this, and then we put it in the next one, and then so then we can write down this C dt using 1 plus Z and then H, Hubble parameter. Okay. Okay. Then we need to integrate. So if we integrate, actually it becomes something like this. So co-moving distance, maybe it's easier. Now this is, you can see this is 1 over Hubble parameter, right? Except C times 1 over Hubble parameter, right? So 1 over Hubble parameter, you integrate, that gives you co-moving distance. And then Hubble parameter, you can write it down also with a cosmological parameter. Okay. So this is actually this is a definition of how to calculate the co-moving distance. So you use mathematical and put this in, and then you can calculate the distance. You don't do this by hand, right? You use computer to do this already. It's too complicated. So, but okay, it makes sense, right? Hubble parameter is this slope. So it's kind of saying the speed, expansion speed of the universe. So you take the inverse and integrate, that gives you the distance. So that actually makes sense in terms of our interpretation. Okay. Okay. If you want to get a distance, you do velocity times time, right? And you get the distance, right? That's what this is saying. If you want to get distance, velocity times, velocity here, 1 over 8, and then integrate. And then that gives you the distance, right? It makes sense, right? And then, okay, then if you, okay, then let's look at simple case. So you put omega lambda equals 0, omega matter equals 1. This is Einstein the universe. It's just omega matter, dark matter, and then you put this number and then you get this. Okay. Okay. Here's very interesting. And then now I have a quiz for the next person. Who is next? So now, question 1. Say Hubble parameter of 100 or 50, which universe is larger? Okay, so now we got this, and if you make redshift infinite, then that gives you the size of the universe, right? So if you make this inverse, this gives you the size of the universe. And then now Hubble parameter is 100 or 50, which universe is larger? Dilution. Yes, that's right. That's right. You're so smart. Because this is, please be careful, this is inverse, right? So 50 is larger. But when I was a student, my professor always get confused. Oh, Hubble is larger. Okay, universe is larger. And I was always telling professor, no, professor, it's the opposite. But, okay, you're laughing now because now I show you this, but so you're laughing. But then a lot of people confuse this, right? Because oh, bigger Hubble or maybe bigger, right? It's people forget it's inverse. So. Okay, then now, okay, something very interesting happens. So now we can calculate the size of the universe, right? By in this definition. So let's do that, and then we can finish it there here. Okay, so now, okay, now we can do this. Okay, we already did this already today, and then so we came to here, right? And then z go infinite, so we drop this gonna be 0, as Zishan was saying, and then, so now 2c divided by 0, this is the size of the universe. Let's calculate, right? And then you put numbers, speed of the light, and the Hubble parameter, something like 70, and then you get 8,300 co-moving megaparsec. That's the size of the universe. Okay. But this is in case of Einstein universe, when there's no dark energy, right? And then what happens if there's dark energy? Okay, if you put dark energy, it's going to be about 3.53 C over H0. That's the size of the universe. Okay, and then now, so that's the size of the universe. Okay, then we ask, at the edge of the universe that we just calculated, how fast the universe is expanding? That's an interesting question to ask. And then let's see. Does it take time? Okay, okay, I'll just quickly do this. But then, if we want to calculate the velocity, you remember this, right? Velocity is Hubble times distance, right? This is right. And then this distance we just calculated, right? That's 3 point something. So we just multiply by Hubble constant, and then we get the velocity, expansion speed of the universe. Let's do that. So that's what I'm doing here. here. So just the distance times Hubble parameter gives you the velocity. And then what's the velocity? Because h0 is the rate of the expansion of the universe. So let's multiply this 3.53c divided by Hubble and then multiply Hubble parameter. So we got the expansion speed of the universe. Expansion speed of a universe is 3.5 times speed of the light. Happy? Happy? Is this okay? It's expanding 3.5 times faster than speed of the light. Is that okay? If you remember that Einstein said in general relativity, the fastest thing in the world is the speed of the light, right? But this is 3.5 times speed of the light. Is that okay? No? Is it okay? Okay, maybe we stop here, okay? If you want to know the answer, please come back next week. Is that good? To be continued. How's that? Okay. Maybe you think about it, explanation. Okay. Okay. So we stop here and then let's have 10 minutes break. Okay. We stop here. Bye-bye.